Welcome to all in the lecture of functional analysis. Now in this lecture we see Euclidean space Rn is a Banach space with the norm of x is equals to summation i's running from 1 to n mod of xi I square whole to the power 1 by 2, where x is equals to sequence xi i's running from 1 to n with the element of Rn. Now let's see the proof of this theorem. Euclidean space Rn is the set of all n tuples of real numbers, that is Rn be the set of all x such that x is equals to xi1, xi2 up to so and xi where each xi I is a real number for all I is equals to 1 to up to so and n. That is, Euclidean space Rn is the set of all n tuples of real numbers. On this Euclidean space Rn, we define the norm like this. Norm of x is equals to summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. To prove that Rn is a Banach space, firstly we show that the norm defined this satisfy all the properties of a norm. We know the properties of the norm. First property of the norm is that norm of x, it is greater than or equals to 0. Second property of the norm of x equals to 0 if and only if x is equals to 0. Third property of the norm of alpha x is equals to mod alpha into norm of x. And the fourth property of the norm, that is the triangle inequality, norm of x plus y, it is a lesser than or equals to norm of x plus norm of y. Now here we have to show that the norm defined on Rn satisfy all the four properties of a norm, and then we say that Rn with this norm is a norm linear space. So let's start the first property. Firstly, we show that what we have to show, norm of x greater than or equals to 0. Here x be the sequence of xi I is running from 1 to n belongs to Rn, be any element of Rn. Now here by definition norm of x is equals to summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. Here we observe that for each I xi I is a real number, and therefore mod of xi I, that is the absolute value of xi I, it is always greater than or equals to 0, and therefore its square, which is always positive, mod of xi I square, that is its square, is also greater than or equals to 0. That means square is always non-negative, and as mod of xi I square, it is greater than or equals to 0, and this is true for each I. That means for all I is equals to 1 to up to so and n, and therefore for each I mod of xi I square is greater than or equals to 0. It means that summation I is running from 1 to n mod of xi I square, that is the sum of all positive non-negative terms, it is also greater than or equals to 0, because each term is non-negative, therefore the summation is also non-negative, and therefore as this term is non-negative, therefore its square root, that means whole to the power 1 by 2, it is also greater than or equals to 0, and this is nothing but norm of x. So we get that norm of x is greater than or equals to 0. In this way we satisfy the first property of a norm, that is norm of x greater than or equals to 0. Prove the second property of a norm. The second property of a norm is norm of x equals to 0 if and only if x is equals to 0. Now we start with norm of x is equals to 0 implies that, here we are putting the value of norm of x, that is equals to this, implies that summation I is running from 1 to n mod of xi I square whole to the power 1 by 2 equals to 0. Now the square root equals to 0, it implies that the term must be equals to 0, and it implies that summation I running from 1 to n mod of xi I square equals to 0. Now this is the sum of mod of xi I square equals to 0. Now in this sum, each term is a square and therefore it is always greater than or equals to 0. That means it is a non-negative term, and therefore the sum of non-negative term is equals to 0. It implies that each term must be equals to 0, and therefore we are writing mod of xi I square equals to 0 for all I equals to 1 to up to so and n. Now the square equals to 0 implies that the term, that is mod of xi I equals to 0 for all I equals to 1 to up to so and n. Now the absolute value equals to 0 implies that xi I equals to 0 for all I equals to 1 to up to so and n, and therefore each xi I is 0. It implies that x is equals to the sequence xi1, xi2 up to so and xin. Now here xi1 equals to 0, xi2 equals to 0 up to so and xin equals to 0, and therefore we writing x is equals to 0, 0 and up to 0, and therefore x is itself 0. We start with that norm of x equals to 0, and it implies that x equals to 0. Now we see the converse part. When x is equals to 0, that means all the coordinates must be 0. That means xi1 equals to 0, xi2 equals to 0 up to so and xin equals to 0. This implies that each xi I equals to 0 for all I equals to 1 to up to so and n. Now each xi I is 0 implies that its absolute value is also 0 for all I equals to 1 to up to so and n. Each term is 0, therefore its square is equals to also 0 for all I equals to 1 to n. Now the term mod of xi I square equals to 0, therefore the summation of all these terms, that is summation I running from 1 to n mod of xi I square, that is also equals to 0, and when this sum equals to 0, its square root is also equals to 0. But now the term summation I is running from 1 to n mod of xi I square whole to the power 1 by 2, this is nothing but the norm of x, and therefore we get that when this is equals to 0 implies that norm of x equals to 0, and therefore here we get that norm of x equals to 0 if and only if x is equals to 0, and that is our second property of a norm. So the norm defined like this satisfy the second property of a norm. Now we prove the third property of a norm, N3. In this property we have to prove that norm of alpha x is equals to mod alpha into norm of x. As here x is equals to sequence xi I is running from 1 to n. Then in this case we write norm of x is equals to summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. So here we have to consider norm of alpha x, and therefore in this case alpha x equals to sequence of alpha xi I is running from 1 to n. On alpha x, the norm is norm of alpha x. It becomes summation I is running from 1 to n. Now instead of xi I, we write down alpha xi I mod of alpha xi I square whole to the power 1 by 2. It is equals to summation I is running from 1 to n mod of alpha square into mod of xi I square whole to the power 1 by 2. Now here this alpha is independent of I, so we can take it out. That is equals to mod alpha into summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. And this is nothing but the norm of x. Therefore, it is equals to mod alpha into norm of x. We start with that norm of alpha x. Then by applying the definition, we are getting that it is equals to mod alpha into norm of x. So the third property of a norm is satisfied. Now we have to see the last property, that is the triangle inequality. Now we prove the fourth property of a norm, that is norm of x plus y is lesser than or equals to norm of x plus norm of y. To prove this fourth property, here we require Cauchy's inequality, and that Cauchy's inequality is that if x is equals to the sequence xi I and y equals to the sequence eta I, then summation I is running from 1 to n mod of then summation mod of xi I into eta I, it is lesser than or equals to summation mod of xi I square whole to the power 1 by 2 into summation mod of eta I square whole to the power 1 by 2. Now here, as our x and y both are the elements of Rn, therefore our x equals to x equals to sequence xi I is running from 1 to n, y equals to the sequence eta I is running from 1 to n, and then our Cauchy's inequality become summation I is running from 1 to n mod of xi I into eta I, it is lesser than or equals to summation I is running from 1 to n mod of xi I square whole to the power 1 by 2 into summation I is running from 1 to n mod of eta I square whole to the power 1 by 2. And here it is equals to norm of x into it is equals to norm of y. That means in Cauchy's inequality we get that summation I is running from 1 to n mod of xi I into eta I, it is lesser than or equals to norm of x into norm of y. This Cauchy's inequality we have to use to prove this inequality, that is norm of x plus y, it is lesser than or equals to norm of x plus norm of y. Now let's start the proof. Consider norm of x plus y. Now here, as x equals to the sequence xi I is running from 1 to n, then here we define the norm of x is equals to summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. When x is equals to the sequence I, then norm of x equals to this. In this way, norm of x plus y, that becomes equals to summation I is running from 1 to n mod of. Now here, instead of xi I, we are writing the as x having the coordinates xi I and y having the coordinate eta I. So therefore, norm of x plus y, that is equals to summation I is running from 1 to n mod of xi I plus eta I square whole to the power 1 by 2. Now taking the square on both sides, we get that norm of x plus y square, it is equals to summation I is running from 1 to n mod of xi I plus eta I square. That is equals to summation I is running from 1 to n mod of xi I plus eta I into mod of xi I plus eta I. This is lesser than or equals to summation I is running from 1 to n mod of xi I into mod of eta I into mod of xi I plus eta I. Here we are using the inequality. If a and b be any two real numbers, then mod of a plus b, that is lesser than or equals to mod of a plus mod of b. We use this inequality here, and therefore we are getting that this mod of xi I plus eta I, that is lesser than or equals to mod of xi I plus mod of eta I into the second bracket is as it is. Now here this is equals to summation I is running from 1 to n mod of xi I into mod of xi I plus eta I plus summation I is running from 1 to n mod of eta I into mod of xi I plus eta I. Now here we apply this Scott's inequality. Firstly, we simplify it. That is equals to summation I is running from 1 to n mod of xi I into xi I plus eta I plus summation I is running from 1 to n mod of eta I into xi I plus eta I. Because here we know that for any two real numbers, mod A into mod B, that is equals to mod of AB. Using this, here we writing summation I is running from 1 to n mod of xi I into xi I plus eta I plus summation mod of eta I into xi I plus eta I. Now here we apply the Cauchy's-Cos inequality, and Cauchy's-Cos inequality says that summation I is running from 1 to n mod of xi I into eta I, it is lesser than or equals to norm of x into norm of y, where the coordinates of x are xi I, coordinates of y are eta I. Now in the same way, applying Cauchy's-Cos inequality, here we get that this is lesser than or equals to, now this xi I is for our x, so we write down lesser than or equals to norm of x into, now xi I plus eta I, these are the coordinates of x plus y, therefore we write down norm of x plus y plus, now here eta I are the coordinates of y equals to the sequence eta I, therefore we write down here norm of y into norm of x plus y. That is, we get that is norm of x plus y square, norm of x plus y square, it is lesser than or equals to norm of x into norm of x plus y plus norm of y into norm of x plus y. Now here norm of x plus y is common, and therefore we write down it is equals to norm of x plus norm of y in one bracket into another bracket norm of x plus y. That is norm of x plus y square, it is lesser than or equals to norm of x plus norm of y into norm of x plus y. As norm of x plus y is always greater than or equals to 0, and therefore we divide on both sides by norm of x plus y, we get that norm of x plus y, it is lesser than or equals to norm of x plus norm of y, and this is the fourth property of the norm and which is satisfied here. So the norm defined on Rn like this: x norm of x is equals to the summation I is running from 1 to n mod of xi I square whole to the power 1 by 2. It satisfies all the properties of a norm and therefore it is a norm on Rn, and with this norm Rn becomes a norm linear space. Norm linear space. Now here we have to show that this Rn is a Banach space. We have to show that Rn is a Banach space. To prove that Rn is a Banach space, that means we have to prove that Rn is a complete norm linear space. Complete norm linear space, and here we prove that Rn is a norm space. Now we have to prove its completeness. To prove that Rn is complete, that means we have to show that every Cauchy sequence in Rn converges in Rn. That is, we have to show. Now we show that the Euclidean space Rn is complete. As we prove that Euclidean space Rn with the norm is a norm space, is a norm linear space. As it is a norm linear space, then with the help of this norm we define a metric on Rn as d of x comma y, it is equals to norm of x minus y, that is equals to summation I is running from 1 to n mod of xi I minus eta I square whole to the power 1 by 2. In this way, we define the metric d of x comma y with the help of the norm. Now, this metric is called as the metric induced by the norm, and we satisfy in the first lecture of the norm that metric induced by the norm satisfy all the axioms of a norm. So it is a metric induced by the norm, and therefore Rn with this metric becomes a metric space. Now we have to show that Rn is complete. So we have to show that every Cauchy sequence in Rn converges in Rn. Let sequence Xm be a Cauchy sequence in Rn. Be a Cauchy sequence in Rn. Then we have to show that Xm converges to X. X must be the point of Rn as m goes to infinity. That means when m goes to infinity, Xm converges to X and X must be the element of Rn. Then we say that, and as we take Xm, Cauchy sequence Xm be any arbitrary Cauchy sequence in Rn, then we get the result that every Cauchy sequence in Rn converges in Rn. Converges in Rn means the point at which it converges, it must be the point of Rn. Then we get that Rn is a complete metric space. So we start with the Cauchy sequence Xm. Xm be the Cauchy sequence in Rn, and that means for all m, Xm is the element of Rn. Now here we are taking m instead of n because here we already use n here. So to avoid the confusion between m and n, so we write down here m. Now Xm is the element of Rn, and every element of Rn is the n tuples of real number, and therefore Xm must be equals to xi1, xi2 up to so and xi n, where each xi I is the real number. Now here our sequence xm, as it is a sequence, then in this sequence we have the terms like this: x1, x2 up to so and in general term xm and so on. So the each xm is equals to xi1, xi2 up to so and xi n. So to represent this m, we write down here xi1m, comma xi2m up to so and xi nm. This m is only for this m. So we have here, if we write down x1, then it is equals to the sequence xi1 m1, comma xi2 1 up to so and xi n1. In this way we write down x1 in the general term xm equals to xi1 m, xi2 m up to so and xi nm. Now here we have to show that xm converges to x belongs to Rn. So we start with the epsilon. Let epsilon greater than 0 be given, and our sequence is a Cauchy sequence. Then by definition of Cauchy sequence we get, for a given epsilon greater than 0, there exists a natural number n0 belongs to n such that for all m comma r greater than or equals to n0, norm of xm minus xr is lesser than epsilon. Now we write down the value of norm of xm minus xr is summation I is running from 1 to n mod of. Now the coordinates of xm are xi im, that is the general coordinate, ith coordinate of xm, minus ith coordinate of xr is xi ir square whole to the power 1 by 2. It is a lesser than epsilon for all m comma r, it is greater than or equals to n0. Now taking the square on both sides, we get summation I is running from 1 to n mod of xi im minus xi ir square, it is lesser than epsilon square for all m comma r greater than or equals to n0. Now here we observe that the sum of the square of mod of xi im minus xi ir, it is lesser than or equals to epsilon square for all m comma r greater than or equals to n0. So the each term of this sum, that is for each I is between 1 to n, mod of xi im minus xi ir square, this term is always lesser than the sum I is running from 1 to n mod of xi im minus xi ir square, and this is lesser than epsilon square for all m comma r greater than or equals to n0, as it is the term, one of the term of this sum, and therefore each term is always lesser than or equals to sum, but this sum is lesser than epsilon square whenever m and r greater than or equals to n0, and therefore we get that for each I, for each fixed I, 1 lesser than or equals to I, lesser than or equals to n, mod of xi im minus xi ir square, it is lesser than epsilon square for all m comma r greater than or equals to n0. Now here epsilon is a positive term, mod of xi im minus xi ir square, it is always greater than or equals to 0. So we take its square root. Taking the square root on both sides, here we get that for each r, 1 lesser than or equals to I, lesser than or equals to n, mod of xi im minus xi ir, it is lesser than epsilon whenever m and r greater than or equals to n0. Now we can write down it as for a given epsilon greater than 0, there exists n0 belongs to the set of natural number such that whenever m and r greater than or equals to n0 imply mod of xi im minus xi ir, it is lesser than epsilon. It is nothing but the definition of a Cauchy sequence, and as each coordinate, that is xi im, xi ir, are the real numbers, therefore it is a Cauchy sequence. Xi im is a Cauchy sequence. It is a Cauchy sequence in R because each term is a real number, and therefore it is a Cauchy sequence in R, and it is true for each I 1 less than or equals to R less than or equals to n. As it is a Cauchy sequence in R and R is complete, so every Cauchy sequence in R converges in R, and therefore the sequence xi im converges in R. That is, we say that xi im converges to xi I as m goes to infinity. It is true for each fixed I that when m goes to infinity, xi im converges to xi I. Now we write down in a simplified form as for each fixed I 1 less than or equals to I lesser than or equals to n, xi im converges to xi I as m goes to infinity. That is, for I equals to 1, we get xi 1 m converges to xi 1 as m goes to infinity. Xi 2 m converges to xi 2 as m goes to infinity. And so on. The general term xi I m converges to xi I as m goes to infinity. And the last term xi n m converges to xi n as m goes to infinity. Now here we say that the sequence xi im, it is a Cauchy sequence in R. It is a Cauchy sequence in R and it converges in R. That means we say that xi im converges to xi I. It is the element of R. It means that this xi1 is the element of R. It is also the element of R. It is the element of R, and this is also the element of R. That means we are getting the real numbers xi1, xi2, xi and xin. Now we collect all these limits. We write down here xi1, xi2, general term is xi, xin. Now, this is the n tuples of real number. We give it the name x, and now this x is the n tuples of real number, and hence it is the element of Rn. In this way, we come to x, that is the n tuples of real number. Now, next we have to show that our Cauchy sequence xm converges to this x as m goes to infinity. Xm converges to x as m goes to infinity. For this, consider here norm of xm minus x. That is equals to, by definition, summation I is running from 1 to n mod of xi im minus xi I square whole to the power 1 by 2. Here as m goes to infinity, xi I m converge to xi I for each I. 1 less than or equals to I less than or equals to n. We prove it. It implies that xi I m minus xi I that converges to 0 as m goes to infinity. And it implies that, what it implies? It implies that the absolute value, that is mod of xi m minus xi I, that is also converging to 0 for each I, 1 less than or equals to I less than or equals to n. This means that the term, that is xi I m minus xi I, that goes to 0 as m goes to infinity. And when this term goes to 0, it implies that norm of xm minus x, that is also converged to 0. That is, as m goes to infinity, norm of xm minus x that goes to 0, because the term, that is general term xi I m minus xi I, that goes to 0 as m goes to infinity for each I, and therefore we get that norm of xm minus x that goes to 0 as m goes to infinity. And it implies that xm minus x converges to 0 as m goes to infinity. It means that xm converges to x as m goes to infinity. Thus we start with the Cauchy sequence. We start with the Cauchy sequence xm in Rn, and we get that xm converges to x and x is the element of Rn. That means the Cauchy sequence xm in Rn converge to x, x is the element of Rn. That means every Cauchy sequence in Rn converges in Rn, because here we take xm be any Cauchy sequence in Rn, and therefore we get that Rn is a complete metric space. And also we prove that Rn is norm-linear space. Thus, from these two, we get that Rn is complete norm-linear space. That is, Rn is a Banach space. This is the first example of the Banach space, that the Euclidean space Rn is a Banach space.